Section 3.3, differentiable functions. A function f is considered differentiable as by definition is if this particular fraction exists as the limit. That is, the limit as t goes to x of ft minus fx over t minus x exists. If this limit exists, then we define the function f to be differentiable at the point x. Now, another way of saying this is that if we let t equal to x plus h and plug it in here, it's just another way of saying if t is x plus h, t goes to x is the same as saying h is going to 0. And then so then you plug t as x plus h and you get something like this. Fx plus h, okay, t becomes x plus h, minus fx over h, t minus x is just h, and as h approaches 0, that if this limit exists, then f is said to have a derivative at x. The reason we have two different looking formulas for the same thing is because sometimes this formula works better for proving certain results, and sometimes this formula works better, and we will demonstrate that right now. The first thing we're going to show is the derivative of a function that's x to the power n, where n is a positive integer in this case. To calculate the derivative of any function x to the power n, we will do exactly as by the definition. So f of x equal to x to the power n. That means f prime of x, by the first definition, this one right here, we'll copy it down, is limit t goes to x of, okay, plug t for x, so we have t to the power n minus x to the power n divided by t minus x. Now, to calculate this limit, we have to use a certain formula to factor this thing. And this thing factors in a convenient way back from algebra. It says whenever you have this kind of stuff, then it factors out like this, t minus x, and then the rest of it becomes t to the power n minus 1. I'm quoting a formula from algebra. If you don't remember this, just believe me. This is how it works. T minus 2 times x, and you keep going, t minus, and anyway, you just keep going all the way. Okay, you keep going all the way down to tn minus n, which is just 0. That's 1 to the x to the power n minus 1. So the whole thing is symmetrical. X goes up 1 power at a time, while t goes down 1 power at a time, all the way down to 0. And the total number of terms here, let's see, it goes from 1 all the way to n. So there are n terms in this thing. And of course, they're still dividing by t minus x. And notice how convenient this is. Because this is identical, we can cancel it out because t is only approaching x. It is not equal to x. So we can do cancellations. So that will equal to the limit as t approach t. Now we let t becomes x in the approach x in the limit. So then t becomes x, and there's n of these things. Okay, and each one n minus 1 times 1 of here. So each one becomes n minus 1 power as t becomes x in this whole deal. So we have a total n of them. So t becomes x. So the whole thing becomes x to the power n minus 1. And there's n of these things. So the answer would be, as t goes to x, is the f prime equals to nx n minus 1, which is what we're claiming right here. Now this formula needs to be memorized, okay? Because in differentiation, we do this all the time. So you really need to remember how to do it. As an example, for example, let's say we have a problem that says v equal to s to the power 3. Never mind what these symbols represent. The point is that's your formula. So what is the derivative of v with respect to x? That is, what is dv by ds? Now remember, dv by ds is the same as saying prime. Okay, we can also call it v prime. They're the same thing. we use that to denote the derivative. The reason there's more than one way to say it is sometimes more convenient to write it this way and sometimes convenient to write it this way, but they mean exactly the same thing. So anyway, dv by ds by this formula is you just take the power on top, the n, which is 3, okay, write down the value here, and then 1 less, n minus 1, n is 3, so n minus 1 is 2, and that's the derivative of this thing. So anyway, this formula has to be crammed in very tight in your brain if you're going to do differentiation in calculus. And now the next thing we're going to do is the sine of x, calculate the sine derivative of the sine. In order to do the derivative of the sine, we have to recall two old formulas, two old limit values. This one right here, the limit of sine of h over h as h goes to 0 is 1. That's been done before. And we're not going to redo it. If you don't remember that, just believe me when I say that. Okay, sine h over h as h goes to 0, it happens to be 1. Similarly, the cosine h minus 1 over h as h goes to 0 is 0. Again, we've done that before. But it's a good idea to memorize this formula, by the way, because it comes up once in a while in proving of this type of thing. And it comes in pretty handy. This one doesn't show up as often, but we're going to need it for finding the derivative of sine x. So to do the derivative of sine x, we will use the second form of the limit definition. So let's do that. F of x equal to sine x. Okay, what is f prime? What is the derivative of f? The derivative will go by the second definition, which is the limit as h goes to 0 of sine x plus h minus sine x divided by h. All right. Now to do this, sine x plus h is something that you have to come back to trigonometry. What is the sine of two angles added up? The formula for that is equal to sine A cosine B. This may or may not sound familiar. It doesn't matter. You did it. Trust me. Plus cosine A sine B. This is from trigonometry. Good old trigonometry. And anyway, it equals to this, and therefore we'll go ahead and use that. So that equals to the limit h goes to 0 sine x cosine h plus cosine x sine h minus the sine x here. Okay, that's the first bunch, and that's copy down the rest of it, and all divided by h as h goes to 0. And then we are going to use this formula right here, which is equal to, we'll combine these first two terms. That will be equal to the limit h goes to 0. Combining these two terms, we have sine x cosine h minus 1. Okay, that's the 1 here. And divided by h. We'll break it down into two limits. Because with limits, you can do that. You can just, because limit of the sum is sum of the limits, well, roughly speaking. So, and then this is cosine x sine h. I'm not writing down h goes to 0 every time, but it's understood. Actually, let's write it down. Oh, there's an h here. H goes to 0. I will write it down this time because this is very important. At this point, you are taking the limit of h goes to 0. X is not going to 0. It's not x is a constant for this limiting process, which means that you can take the constant out of the limit. So then it becomes sine x limit h goes to 0 of cosine h minus 1, which is 0, okay, from this formula right here. So we will have sine x times 0, which is what that will become, plus on this side, again, we'll take cosine x out because it is a constant where this limiting is concerned. So the limit as sine h over h is 1, cosine x times 1. And that all amounts to cosine x, because that other part is 0. So that's goners. So is cosine. So the derivative of sine x just happens to be cosine x, which is very, very nice, of all the luck in the world. And then in a very similar proof, you can figure out that the derivative of cosine x will become negative sine x. But there will be a negative sign there because that formula looks a little different for cosines, which we will not repeat. But let me emphasize that these three formulas need to be memorized, damn solid, because that's the only way you can make it through differentiation.